Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to look at one of the processes of energy changes in physical and chemical processes, and that is the concept of enthalpy of solution. Now we know that whenever we dissolve maybe some of the salts that we come across, especially during chemical analysis, some of them dissolve to form solutions. So these processes may be accompanied by a change in energy, and therefore this process that we're going to do today entails the aspect of trying to do an analysis or maybe trying to quantify the heat energy that is involved. Now I've given two specific illustrations on the board. We're going to use them in our specific discussion for this particular topic and try to see how we can be able to handle problems of that nature. So for that case, thank you and welcome. So say today we're going to rely basically in trying to find out how we can be able to find the enthalpy change of solution. And this comes from the fact that we had already discussed some of the concepts which led us to the concept of enthalpy. And we say that the heat content in chemicals are basically what we refer to as the enthalpy. So enthalpy basically refers to the heat content of a chemical. And we say that it is basically not possible to measure the enthalpies of chemicals. However, since we know that this specific change in energy is accompanied by a change in temperature or result in change in temperature, we therefore be able to measure the change in temperature, which will basically give us the concept of the energy changes in that specific maybe reaction of a chemical. So we said that we are going to denote this change in enthalpy using delta H, which is given as delta capital H. So this basically means change in enthalpy and this enthalpy, as we said, is a change in energy change, and therefore we said that the equation for enthalpy change can be given as this is a delta H can be given as or is equal to enthalpy, or we can just give an initial using, since it's a form of energy change, enthalpy of the product, where E implies enthalpy minus enthalpy of the reactants. So this basically forms the anatomy of a chemical equation whereby we have reactants forming products. So therefore this is the general equation for representing enthalpy as we discussed. And we said that the energy change which is associated with a chemical change can be shown in a stoichiometric equation of chemical reactions, whereby we have the symbol change in enthalpy, which is preceded by the amount of energy that is used, maybe in kilojoules. And in this case, if it's maybe a mole of a substance that is being referred to, then we can say that it's kilojoules per mole. But since that is the form of energy, we are just going to give it in form of kilojoules. So now, depending on other conditions like maybe the mole that I've talked about, there are other emissions that we're going to just write accompanying that specific case. And we said that there are two forms of reactions during this change in energies, whereby a change in energy can be accompanied by the release of heat from the system to the surrounding. So my handwriting, I hope it's legible. This is a surrounding. So therefore, this process whereby there is a release of heat from the energy, which is basically entailing the aspect of chemicals which are reacting in this particular system, is referred to as exothermic, where the reverse of taking heat from the environment, from the surrounding to the system, is referred to as an endothermic reaction. So basically, these particular two specific reactions can be given a symbol which is going to portray the aspects of losing energy from the system. So with respect to the system, if heat is lost to the environment, we're going to give it a negative notation, which precedes maybe the quantity of heat which is involved. So in any case, if I'm going to give a delta H, which is negative 80, then this specific symbol implies that that specific reaction is an exothermic, And if I give it a positive symbol, then it means that reaction is endothermic heat is being taken into the system, and therefore that is going to be noted using positive 80 kilojoules. And that is a short summary of what we have discussed. And lastly, maybe I'm just going to give one illustration for thermochemical equation, which is showing enthalpy change. So we said that if we have two compounds or maybe two elements, like the two diatomic gases which are reacting to form ammonia, and in this case we should ensure that the equation is stoichiometric in the first place. So in this case I've just written this coefficient for 2 in order to balance that. So we write this symbol giving the delta H as just an hypothetical figure, maybe could be true, but let me just give it this. So this implies that the enthalpy change in this specific kind of a reaction is an exothermic, having seen that it's given a negative notation in this specific way. So therefore we are going to use this specific concept. Now from the Avogadro's constant and the mole concept, we are also going to infuse some concepts of the mole. Suppose we know the amount in maybe the mass of this specific reactants which is being used, and therefore we can be able to calculate the amount of heat that is used, maybe reacting a mole or forming a mole of a substance of either the product or maybe what kind of how many number of moles of a product or a reactant that is needed to form the product. So in this case, basically our illustration for today is going to rely heavily on those two concepts, and I hope having given a summary of what we need for that to be easier for us to discuss. So in my illustration I've given two tables. I mean just a single table for the sample results, and this is an illustration since we could not be able to perform an experiment. So this illustration is going to give us in an essence a way in which we are going to do a reference from that. So basically in my table I've got ammonium nitrate and sodium hydroxide as my two substances. Tf refers to the temperature final, temperature initial, and change in temperature. So we are trying to find the enthalpy change in this specific setup. So I have setup 1 and setup 2. So these are similar setups, only that there's a difference in the amount of, I mean the nature of the substance that is used. So in our first experiment, this is a 2.0 ammonium nitrate. So 2.0 grams of ammonium nitrate that is being dissolved in 100 millimeters of water in a beaker, and then the temperature is used to stir. I mean the initial temperature will be taken in this case, and then the final temperature as well will be taken after the experiment, and then we will find out that what's the change in temperature in that case. So maybe I will just change this one because of space. So this is ammonium nitrate. So just change this one. So therefore I'm going to have this table illustrated as that, because this is one that is showing what aspect we're trying to measure. So in that case, this is the specific setup. So for the first one is ammonium, or maybe I can just just say this is a setup A. It's just because we just already changed the table. So for that case, we are going to use the two illustrations. So I'm going to use sample results for us to just have a discussion about the one that we have already illustrated on the board, as I've said, since we could not be able to do the experiment. And in this case, for ammonium nitrate, when 2 grams were dissolved, it was found that there was a temperature, the initial temperature reading was 23 degrees centigrade. Now that is for ammonium nitrate, and after dissolving that and stirring it with the temperature, the final temperature was recorded to be 21.5 degrees centigrade. So in this sense, we're trying to find we're trying to observe that there is a decrease in temperature when we are trying to dissolve ammonium nitrate in 100 millimeters of water. So in this case, we're seeing that there is an intake of heat from the surrounding into the system. And therefore there's a connotation we give for that specific phenomenon, whereby heat is taken away, taken from the surrounding into the system, thereby giving it, the surrounding, a cold or maybe a drop in temperature. So therefore this kind of a reaction, we can just give it a notation for either endothermic or exothermic. So therefore this is going to form an endothermic reaction, since there is a drop in temperature whereby the system takes in temperature from the surrounding. So the change in temperature for our case here is going to be 1.5, and we are going to see that this is degrees centigrade. So for ammonium nitrate, I'm going also to give a sample result for that. So the initial temperature was 22.5 degrees centigrade. 22.5 degrees centigrade, and the final temperature was recorded to be 27.5 degrees centigrade. So in this case, we're seeing a reverse of this particular case happening, whereby there's an increase in temperature from 22.5 to 27.5, and therefore the change in temperature in this case as well was 5 degrees centigrade. There was an increase in temperature in the surrounding. So therefore, which means heat was evolved or dissipated from the system to the surrounding. We can just use that arrow to imply loss of heat from the system to the surrounding. So basically now I can just use this remaining space here to imply that the taking in heat from the system to this, surrounding to the system, is endothermic. And for the second case, in our case for the first one here for ammonium nitrate, heat is dissipated or given out from the system to the surrounding, and therefore this is an exothermic reaction. Therefore, depending on our sample results that we have given, we can see that there are two different kinds of reaction which are taking place in dissolving those two different substances. And therefore, from our information that we are going to use, maybe we can be able to calculate the enthalpy change for those two experiments. Now, we have been mentioning the change in enthalpy being given as a delta H. Sorry for that. Being given as delta H, just trying to minimize space. So this delta H has got a formula, and it can be given as mass mc delta T. So this one implies mass, and this one implies specific heat capacity. Now when something is specific, it implies that different substances have a unique quantity of that particular kind of a measure. So in this case, we are also going to see that the delta H that we're talking about here, this is the change in temperature. So therefore, we're going to have a reading for this specific heat capacity. Now in this case, we are going to see that to calculate the enthalpy in pot 2 of our sample experiments, we're going to assume that the density of the solution is equivalent to the density of water. So I'm just going to write that condition here. So the density of that particular solution is the density of water, which is 1 gram per milliliter or 1 gram per centiliter cubed. And the specific heat capacity for water, which is C, is given as 44.2 kilojoules per kilogram per Kelvin. So therefore the temperature that we have been using for degrees Celsius, we're going to use it, the Kelvin scale, having been given these dimensions for C being given in kelvins. But we're going to see that the change in temperature, delta T, is just the same for the degrees centigrade and for the Kelvin scale. So a change in temperature between 273 kelvins to 373 kelvins is equivalent to a change in temperature from 0 degrees centigrade to 100 degrees centigrade. So this one implies that a change in temperature, which is 1 Kelvin, is equivalent to 1 degrees centigrade. So therefore, using that conversion factor, we are just going to use the quantity, the absolute value of that change in temperature in this case. So therefore, for us to find the enthalpy change for ammonium nitrate, so we shall start with the first one, which is ammonium nitrate. So we want to find the enthalpy change of dissolving ammonium nitrate in 100 millimeters of water. Therefore, we'll write it as the mass. So in this case, we're going to consider the mass of the solution, which is basically the mass of water. So therefore, we know that mass is equal to density times volume. And the density we have been given as 1 gram per centimeter cubed. And the volume, or per milliliter, we just use the one which has been used. Yes, so we know that the volume that was used is 100 milliliters. So therefore, the density in this case is going to be 100 grams, which is equivalent. So we can convert it into kilograms so that those dimensions are going to be easier for us to make calculations. So this is 0.1 kgs of the mass of the solution. So the temperature change for nitrate, the ammonium nitrate is 1.5 degrees centigrade. So we're trying to look at this different aspect of this formula in order to find the solution for that. We have been given C as 4.2 kilojoules per kilogram per Kelvin. So therefore, I said that the change in temperature in degrees centigrade is equivalent to change in kelvins. So that's not going to give us a problem in that case. So therefore, we are just going to do a substitution to see what amount of heat was absorbed from the surrounding into the system. So therefore, the delta H is going to be given as mass 0.1 kgs times the specific heat capacity 4.2 kilojoules per kilogram per Kelvin times change in temperature 1.5 Kelvin. So this Kelvin is a reciprocal, so in this case it's going to go, and then we have a kilogram per kilogram is going to go. So the amount of heat that we are going to find is going to be given in terms of kilojoules. So if we do a calculation for this, we can just do a confirmation. In any case we come across maybe a variation, we can just do that in our comment section. So I have 0.63 kilojoules for the heat that was absorbed into the system. So in this case, basically that's how we can be able to use this formula in order to find the enthalpy of solution in this case. Now for this case, because the heat was taken into the system, it's going to be a positive value. So therefore that figure is correct by our calculation. So the same way we are going to use the concept, this similar concept in trying to find the heat, the enthalpy of solution of our sodium hydroxide. So therefore we're going just to do a substitution again for that and try to figure out how much it is. So having used 100 millimeters, so therefore the mass still will be the same as 0.1 kgs as per the one that we used there. So we said we assume the mass of the solution has got a density of the density of water, and the specific heat capacity still we're going to take that one of water. Therefore we're going to have delta H given as 0.1 kgs times the specific heat capacity for water per Kelvin times the temperature change, that is going to be 5 kelvins. So I just given this specific dimension for easy calculation. So this is going to be 2.1 kgs, kilojoules of heat. But remember, we said that this heat is being dissipated, so therefore this is going to be a negative value. So the delta H for sodium hydroxide is going to differ with the one with ammonium nitrate by this negative value. And from this case, I mentioned the concept of the mole concept, which we can be able to infuse in this concept and try to figure out what amount of heat can be used by a mole of these specific substances. So we have said that we dissolved 2 grams of each individual substance that we have mentioned. So suppose we are asked to calculate the number of moles of a solid that it is dissolved in this experiment. We are going to see that for 2 grams of ammonium nitrate, we can find the mass or the number of moles by taking the mass in grams per liter divided by the relative formula mass, or maybe just the mass over RFM, which is the grams used 0.2 grams all over. The relative formula mass for that, this is 14 times 228 plus 432 plus this is 16 by 3, 48. So this is going to be 80, this is correct. So this is 80 grams per mole. So therefore, sorry for that. So this is going to give us 0.025 moles of ammonium nitrate that were used. And this is contained in this space. So 0.025 moles of ammonium nitrate. This one was able to absorb 0.63 kilojoules of heat. So therefore we can just do a comparison and say 1 mole so that we can find the heat in kilojoules per mole. So this is going to be 1 times 0.63 divided by 0.025. Just left out the units because of the space. So therefore this is going to give us 25.2. Can just do a confirmation for that. 25.2 kilojoules per mole. So therefore that is going to form enthalpy that is used in the experiment of a mole of this specific solute. So therefore we are just going to use the similar procedure in trying to find out the number of moles of sodium hydroxide that were used. But remember the designation for the positive or negative sign in this case, which is very important to imply that either the reaction is endothermic or exothermic. So therefore this is the way in which we're going to find out other enthalpies which may be involving different kinds of reaction. As I said that our main topic for today was enthalpy of change of a solution. Now we have different kinds of reactions of chemicals, and we can maybe discuss, as I said, about the concept of combustion, displacement, neutralization, like the acid base that we have discussed in titration, etc. So these reactions are going to be accompanied by energy, which we can represent in this specific form. Now I hope that given a challenge that is similar to the one that we have discussed, one can be able to find the enthalpy change of solution using the specific steps that we have used in these 2 particular setups. So I hope that this is going to assist us in trying to figure out how we can handle challenges of a similar case, and maybe the other questions that we are going to discuss after. So that is it for today, guys. Bye. God bless you.